These are the notes for AP Calculus on the topic of volume using the shell method. So consider the area bounded by the graph of the function f of x, which is just a parabola here, x minus x squared, and the x-axis. So if we take this region right here, and if we revolve it around the y-axis, we can see we'll get this three-dimensional shape here. And if we look at how we're going to do this mathematically, if you take your representative rectangle right here, and we'll take an infinite number of these rectangles, but just look at one for it right now. And if you revolve it around the y-axis, you can see it creates this cylinder-like shape, which is called a cylindrical shell. So you can think of this in the green here like kind of like a cardboard paper towel or toilet paper roll. And what we're looking at is the volume of the cardboard. So if we take that and slice it vertically and then unravel it, you can see to get the volume of this, we would take the height right here, and then this part here is just the circumference of the circle, 2 pi r, and then the thickness dx right here. So what this would look like, we've got a bunch of these different rectangles here, and using calculus they'll be infinitely thin, but we'll just look at some finite ones here. If you revolve it around the y-axis, we get these cylindrical shells one inside of another to create that three-dimensional shape, like that. So the formula, using the shell method then, really comes from the same thing as the surface area of a cylinder. You got 2 pi times, in this case we're calling the radius p, times the height times dx. So that's what we have in our formula for the volume. You can factor out the 2 pi, well, the constant on the outside of the integral, and integrate from a to b wherever your region starts, wherever it stops. And then you've got p of x, which is the radius, and the height h of x. So let's take a look at a problem similar to the example we just looked at visually. It says find the volume of the solid of revolution by revolving the region bounded by y equals negative x squared plus 6x and y equals 0 about the y-axis using the shell method. So the first thing you could do, so we're going to do this one without a calculator, is to figure out where these two intersect. You can just set them equal to each other. So if we set negative x squared plus 6x equal to 0, if you factor out a negative x, that leaves you with x minus 6. So yeah, either x has to be 0 or x minus 6. If we set that equal to 0, we give you x equals 6. So those are the two places they intersect. And we already know the y equals 0 is just the x-axis there. So if we graph that one, okay, so there's y equals 0. And we know they intersect at 0 and 6. So right there, 0 and at 6. And if you take a look at the equation here, this is going to be an upside down parabola. So we really don't need a perfect graph of this. We know it goes through those 2 points. So we can just do a rough sketch of it like that. That's enough to see the region enclosed. And then what we're going to do is take this and it says we're going to revolve it about the x-axis. Sorry, about the y-axis, I should say. So you can put a little circular arrow there to show that's what it's revolving around. And then we can draw our representative rectangle somewhere in here. This region enclosed. That is dx. And then what we want to find here is the radius and the height to set this up correctly. So we can actually draw this cylinder here wrapping around the y-axis to give us an idea of what the radius and height would need to be. So that just represents that one cylindrical shell using this rectangle. And the height, you can see, is just the distance, just the length of your rectangle. So just from there to there. It's h of x. So the height, h of x, just like you would do the area, is the top function minus the bottom function. In this case, the function on the top is negative x squared plus 6x. And minus the function on the bottom of that rectangle is 0. So there's your height. And then the radius, you can see, just goes from the axis of revolution to the rectangle. So that would be the radius of our cylinder, which we're calling P of x. And to figure that out, just think, well, the coordinates of this point, right here, no matter where you drew your rectangle, you can represent the coordinates as x, y. And notice from there to there, no matter where you drew the rectangle, that's just the x coordinate, is the distance. So your radius, P of x, on this example, would just be x. So to find the volume, let's go ahead and set up the integral. The integral from the region here starts, the x-coordinate starter set is 0, and stops over here at 6. So from 0 to 6, you have 2 pi on the outside for the shell method. And then you just have the radius P of x times the height, which is h of x. So just x is our radius P of x, and the height was negative x squared plus 6x times the thickness dx, turns it into volume. So we just have to integrate this. This one we'll do without calculator. So leave the 2 pi on the outside. Integral from 0 to 6. And if you just distribute out that x, we get negative x cubed plus 6x squared. And now we're set to integrate that. So we have 2 pi on the outside. When you integrate that, the negative stays out front. When you integrate x cubed, that would be x to the 4th over 4 plus 6x cubed over 3, evaluated from 0 to 6. Yeah, 2 pi and then we've got negative 6 to the 4th over 4 plus 6 times 6 cubed over 3. And you plug in 6, and then when you plug in 0, you just get 0 on both of those. So to figure this out more easily without your calculator, there's a couple of different ways you can do this. I'm just going to, along with the 2 pi, 6 to the 4th is pretty big, so I'm just going to pull out 6 cubed, factor that out of both terms, so I can figure that out more easily. And then what we'll be left with is negative, there'll be 1/6 left here over 4, plus there'll also be 1/6 here over 3. A little bit easier to work with. So we've got 2 pi times, well, 6 squared is 36 times 1 more 6. Gives you 216. And that's negative 3 halves. Reduces 2. And that's 2, 6 divided by 3, which to get a common number would be the same as 4 halves. And negative 3 halves add up to be just 1 half. And then the 2's reduce to just give you 216 pi. And since we're talking about volume here, it would be units cubed. You don't have to put that because it's not specific units, but it is in 3-dimensional. Okay, let's take a look at another example now. This we're going to do with calculator. So it says, find the volume of the solid revolution by revolving the region bounded by f of x equals 7 arctangent of x minus 2 and g of x equals x squared minus 8x plus 18. About the y-axis again, we'll use the shell method here. So let's go ahead and enter these in our calculator. Again, first I'll show it on the TI-84. So let's enter these in. So 7, remember arctangent can also be written on your calculator. Looks like tangent with a -1 that looks like an exponent because it's the inverse of tangent. X minus 2, and then g of x is x squared minus 8x plus 18. And let's change our window size here. Let's make it x minimum -8, x maximum 8, and y minimum -1, y maximum 10. And when you're doing this on your own here, if you're not given this graph outline, you're just basically going to need to just kind of play around with your window size until you can see the region enclosed. So let's graph this. Okay, so there's the graph of f of x, and there's the graph of g of x. So it's graphed on our calculator, but just still a good idea to graph it on paper as well to make sure you get everything set up correctly. So again, you don't need a perfect graph, it's just a rough sketch. So f of x we can see something like that. And g of x is our parabola, something like that. Yeah, so there's a rough sketch of our region enclosed in. And again, we're revolving around the y-axis. So circular arrow there. And again, you can just draw your representative rectangle somewhere in this region. And again, the two things we need to figure out are the radius and height. So we take our rectangle, if you revolve around the y-axis there, we draw kind of roughly what this cylindrical shell will look like. Let's figure out the radius and the height. So the height, you can see, goes from here to here, which is again just the length of the rectangle, but same thing you would use if you were just finding the area. So our height, h of x, again, since the one that is on top of the rectangle has a larger y coordinate, you take that one, which is f of x, minus the one that's on the bottom has a smaller y coordinate, so that's g of x. And since we're just revolving around the y-axis again, there would be our radius, p of x. And again, since that's just some point, no matter where you use your rectangle, you can call that point xy. You can see the p of x, since it just goes right back to the y-axis, is just your x coordinate. So let's set up our integral here. And notice in this case, we also need to find the points of intersection, which if you try to set these equal to each other and solve it by hand, is not easily done. So that's where our calculator is going to come in handy. So let's label our points of intersection. I'll call this point capital A, and this one capital B. So I'll use our calculator to find both of those. See a second calc. Number 5, intersect. First curve is y1, enter. Second curve, y2, enter. Guess, I'm going to guess the first one looks like about 2.5. Or you can move your cursor left and right. And it's at 2.6224884. So write down on paper, as well as storing it in your calculator. So then go second quit. Sometimes you might have to hit the second A and S button first on some calculators. But on the 84 here, I can just go store alpha A. And let's find our other point of intersection. First curve again, y1, second curve, y2. Guess this time I'll just move the cursor over there, close to that point. So B is 6.7462686. And then let's store that in our calculator. So we can quit, store alpha B. Alright, so now this is in our calculator, so let's go ahead and set up our integral. So again, with the shell method, we've got 2 pi on the outside, because again, it's just coming from the surface area of a cylinder, the part that wraps around. It's 2 pi RH. And then the integral here this time, our region starts at the x-coordinate of A, and the region stops at the x-coordinate of B, so from A to B. And then it's just the radius times the height. So the radius was x, times the height was f of x minus g of x, all times dx. So let's go ahead and use our calculator to evaluate that. So we can, so you don't forget the 2 pi, you can do that first. 2 pi out in front times, and then math, number 9, function integrate, and we want to integrate is x times, parentheses, and our height was f of x minus g of x. F of x we have in our calculator is y1, so variables, y1 minus variables, y variables, y2, and then close parentheses, then comma, our variable is x, comma, lower limit alpha A, comma, upper limit alpha B. And then just be accurate to 3 decimal places, so we get 489.866. And again, it would be units cubed since we're talking about volume here. So not any specific units. Alright, now let's just quickly look and see how you do the same thing on the TI Nspire. So on Nspire, I calculate this. Oops. Just go to a new document, and let's add the graphs first. So our first one was seven arctangent of x minus 2. And then our second one was x squared minus 8x plus 18. And let's change our window size. So menu, window zoom, window settings. Let's Again, go from -8 to 8, x min and max, and y min, let's make that -1, y maximum 10. There we go, so now we have a nice picture of it. And again, to find our points of intersection, we just go Menu, Analyze Graph, number 4, intersection, lower bound to the left of that point of intersection, upper bound to the right of it, and then just highlight that, variable, store variable, A, and to find other point of intersection, do the same thing, analyze graph, intersection, lower bound, upper bound, there's the point of intersection, and you can store that as B. And then document, we'd insert calculator, and then we can set up our integral. Again, don't forget the 2 pi on the outside. And times the definite integral from A to B of x times, open parentheses, our first one was f1 of x minus f2 of x dx. Let's see, we get the same answer, 489.866. All right, let's take a look at the next example. So now let's look at revolving around things besides just the y-axis. So we're going to revolve around x minus 3. And on this one, well, you can really do without your calculator here. So if you just set these equal to each other, or you can just kind of sketch the graph from either way. So if you set it equal to each other, 3 minus x squared equals x plus 1. One side equal to 0, add the x squared over, plus x. If you subtract the 3 from the 1, minus 2, and factor that into x plus 2, x minus 1, and see we've intersected x equals -2 and x equals positive 1. And this one you can just see is going to be a linear equation, x plus 1, with a y-intercept of 1 and a slope of 1, so it intersects there at 1, that's 1 point of intersection right there. And then right down here, another point of intersection. So let's go ahead and graph that one. There's y equals x plus 1. And you can see the other graph is just an upside down parabola here, where the 3 shifts the graph up 3, and the negative in front of the x squared makes it up and down. And we already know these are points of intersection here, so it's just going to curve down like this. And down like that. Okay, so again, we just need a rough sketch of the graph. But this time, notice our axis of revolution is x equals -3. So I'll draw that, this is not the y-axis, as a dotted line over here at -2, so it doesn't confuse what the rigid enclosed is. So that's what we're revolving around. That's not real straight there. looks a little better. All right, so now let's draw a representative rectangle there. And even though you can draw it anywhere in here, it's usually easiest to set this up correctly if you have a choice, if you're able to draw it in the first quadrant. So I'll draw it over here. And we draw a representative cylinder. This time it's not going to run up around the y-axis. It's revolving around the line x equals -3. So try your best to center it around there, just so you can see the height and radius a little better. And so, you see our height, h of x would just be the length of the rectangle again, right there, from there to there. H of x. So h of x will just equal the one function on top, 3 minus x squared. That is the bigger y coordinate. Minus, function on the bottom is x plus 1. Make sure you subtract the whole thing in parentheses. And then our radius, this time is not going to just be x because it doesn't just revolve around the y-axis. So if you look at it graphically, you can see it goes from our axis of revolution to the rectangle. There's our radius. There's a couple different ways you can figure that out. Whichever way works best for you. So one way you can do, kind of like we did the top function minus the bottom function here, because the top function has a bigger y coordinate, you can do the same thing here. Except when you're looking at a horizontal distance, you look at the function that's further to the right first, because that has a bigger x coordinate. So here we'd have x is the one further to the right, minus one over here is -3, which you can see simplifies to just be x plus 3. That's one way to look at it. Another way to see why it would be x plus 3, the way that would make sense, is x represents this distance from a rectangle back to the y-axis, right? When it revolves around the y-axis. And you can see the distance from the line -3 to the y-axis, that distance is just 3. So you can see x plus 3 would make sense for our entire radius. So whichever way is easier for you to think about. Now let's go ahead and set up our integral. And this one we can do without a calculator. So we've got 2 pi on the outside. Integral from the region starts at -2, stops at x coordinate of 1. And then we have our radius, which is x plus 3, times, if we simplify our height there, so that'll be -x squared minus x, and then there'll be a -1, and a 3 gives you a positive 2. Dx. So then we just need to multiply this out before we can integrate it. So if you distribute out the x, so you'll get -x cubed. And then there'll be a -x squared right there. And then a -3x squared right there. Give you -4x squared. Combine all the terms, and then we can see we've got x times 2 is 2x, and -3x gives you -x. And then when you plug in 3, when you distribute out the 3 times the 2, you get 6. And now we can go ahead and integrate it. So we have 2 pi on the outside. And we integrate that, you get -x to the 4th over 4 minus 4x cubed over 3 minus x squared over 2 plus 6x. Evaluated from -2 to 1. Now when we substitute those in, you substitute in the 1, you get -1/4 minus 4/3 minus 1/2 plus 6 minus, we substitute the -2. Well, -2 to the 4th is 16 divided by 4 is 4. That negative makes it a negative there, a -4. Then -2 cubed is -8 times 4 is -32, but that makes it a positive right there. So positive 32/3. And then -2 squared is 4, divided by 2 is 2, -2. And we can substitute -2 there, that's -12. So then, when you're simplifying this, probably the easiest way to do it is combine those terms that already have the same denominator first, if you can. So, let's see, there's nothing really to combine with a -1/4 now. We've got -4/3, and that's going to be -32/3. It'll be -36/3. Nothing really to combine with a -1/2. And then we've got 6. It's going to be a +4, it's 10. That's going to be, this is a -14. That's going to make it a +14. So 10 plus 14, 24. So almost got it simplified now. So now if we just combine the -1/4 and the -1/2, that's in fact -2/4, and -1/4 would be -3/4. And notice this is -36 divided by 3 is just -12. So 24 minus 12 is +12. And then 12 is 48/4 minus 3/4 is 45/4. Then 2 goes into 4 twice. So simplifies to be 45 pi over 2. And again, it would be units cubed. So it takes a little more work when you're integrating when it's not revolving around the y-axis. Because we saw when it's the y-axis, the radius is just x. But if it's not the y-axis, the radius is just a little more complicated. All right, let's take a look at another example. This one, though, we will use our calculator on. So let's go ahead and enter those two equations in. Again, I'll start with the 84. So clear these other ones out. And we've got x raised to the 2/3 and 2 times the sine of x plus 1. And then let's change our window size. -1 to 12 for the x minimax, and -1 to 7 for the y minimax, and graph that. So there's a graph of x to the 2/3. And there's the graph of 2 sine of x plus 1. So you can see the region enclosed right in there. Pretty small region there. So we don't need to graph the entire thing, just enough to see our region there. So f of x, we can graph it on paper, even though we've got our calculator graph it, set it up correctly. Something like that. And the relevant part of g of x, something like that. And this time our axis of revolution is over here at x equals 5. So let's draw that as a dotted line. So that's what we're revolving around. And again, let's draw a representative rectangle. Set this up correctly. Width is dx. And when it wraps around the line x equals 5, we get a cylindrical shell, like something like this. So again, the two things we need to figure out are the radius and the height. So let's start with the height because that's usually the easiest of the two to figure out. And again, you can see the height, just the rectangle. There's our height, p of x. Sorry, h of x. So h of x will just be, again, just like what we used for the area. The function on the top this time is g of x minus function on the bottom of the rectangle is f of x. And then the radius, p of x, let's see if we draw it in there, would be from a rectangle there to our axis of revolution. That would be the radius. So again, there's two ways of thinking about that. One way is to, again, since we're looking in the horizontal direction for the radius, take the function further to the right first. In this case, that's 5. That has a bigger x coordinate. And then subtract the one that's further to the left, which is just x, our rectangles. So we get 5 minus x as a radius. Another way to see that graphically, why that would make sense, again, is if you look at the distance from there to our rectangle, that's the x coordinate, from there to there. And then the whole distance from the y-axis, line x equals 5, is 5. So you can see our radius would be 5 minus x, would be that distance. And again, we're going to need our points of intersection here. So I'll call those again A and B. So use our calculator to figure those out. So let's go ahead and do that on the 84. So the second calc, intersect. First curve y1, second curve y2, guess. I'm going to guess negative 0.5. Which one? And it's a negative 0.6255834. So write it down on paper and then store it in your calculator. Second quit, store alpha A. And let's find the other point of intersection. So second calc, intersect. First curve y1, second curve y2, guess. Move the cursor over here. And that one's 1.4473883. And let's store this in our calculator. Second quit, store alpha B. Alright, now that we've got those points of intersection, let's go ahead and set up our integral and figure out what this is. So on the shell method again, you have 2 pi on the outside. Integral from a region starts at A, x coordinate of A, stops at x coordinate of B. So from A to B. And our radius this time was 5 minus x. And our height was g of x minus f of x. And all times dx. Let's use our calculator to figure out what this integral equals. So again, don't forget the 2 pi. Let's put that first so we don't forget it. 2 pi times math number 9, function integrate, and then open parentheses, 5 minus x, close parentheses, is our radius, times, open parentheses, it was g of x minus f of x was our height, so g of x is y2, so variables, y variables, function y2 minus variables, y variables, y1. Close parentheses. So that's what we want to integrate, comma, the variables x, comma, the lower limits alpha a, comma, the upper limit alpha b. And we get 58.769. Again, this is volume, it is units cubed, although we don't have specific units what those are. All right, now let's take a look at doing the same thing on the Nspire. Create a new document. I'm not going to save this one. If you did want to go back to it later, you could call it something. So I'm going to add graphs, enter in 2 equations here. So there's x to the 2/3 and f2 is 2 sine of x plus 1. Okay, so change your window size. Go from -1 for the x minimum to 12, and y minimum go from -1 to 7. Okay. So again, this other parts are just looking at that region right in there. So then let's find our points of intersection. There's the first one, and then store it as A. And find our other point of intersection. Store it as B. And then let's insert calculator. So again, we can go 2 pi times the integral from A to B. And open parentheses, our radius was 5 minus x times, open parentheses, our height was g of x, which was f2 x minus f1 x dx. So again, you can see we get 58.769, or if you round it, 770. Notice the answers are slightly different. because the calculators are using different methods to approximate this, but they're still accurate within 3 decimal places there. All right, let's look at the next example now. It says, sketch the region bounded by the given equations. Using the shell method, set up the integral to find the volume of a solid generated by revolving the region bounded by the graphs of the equations about the indicated axis of revolution. So this time, notice what's different, we only have one equation. So, and we're revolving around x equals 4. So you might recognize x squared plus y squared equals 4, that's just a circle. Where it's centered at 0, 0, right here. And the 4 is the radius squared, so the radius would be 2. So this encloses its own region, which makes it a little different. We start at 0, 0 and go 2 each direction. Just draw a circle that goes through those 4 points. Let's try that again. Doesn't have to be perfect, mine certainly isn't. But it encloses its own region, which makes it a little different. And then our axis of revolution, x equals 4. You can just draw it as a dotted line over here, over 4. That's what we're revolving around. So you can kind of picture this one, if we take this circle and revolve it around this axis of revolution, we get like a donut-like shape. So, we draw our representative rectangle in here. It will be x is the width. And draw the representative cylindrical shell. That. Let's go ahead and try to get our radius and our height. In this case, the radius might be a little easier in some ways. The radius, you can see, goes from axis of revolution to our rectangle, d of x. So the radius would be the one furthest to the right, which is 4 minus, where the rectangle is x. What's different is the height. Normally, on the height, well, it's still the length of the rectangle, that's still true, so the height goes from there to there. But normally we have 2 different functions. To subtract, but here it comes from the same equation. So what we have to do is kind of decompose this circle into 2 functions, because right now it's not a function. So if you do that, you just solve it for y. So if you subtract the x squared first, so you have y squared equals 4 minus x squared. Then take the square root of both sides. You get y equals, remember, take the square root of both sides of the equation, you need plus or minus square root of 4 minus x squared. So the circle is actually can be made of 2 semicircle functions. The top semicircle there and the bottom semicircle right there. So the one on the top, that's the equation y equals positive square root of 4 minus x squared, because it's positive y coordinates. And the one on the bottom is y equals negative square root of 4 minus x squared. So now we have 2 separate ones. So for our height, h of x, I take the one on the top, which is square root of 4 minus x squared, minus the one on the bottom, which is negative square root of 4 minus x squared. You can see the negatives cancel out and you get plus. So it's actually going to be 2 times the square root of 4 minus x squared. You see why that makes sense? It's really double because of the symmetry of the circle here, what this would be. So this one, if we just went for the height from there to there, it would just be square root of 4 minus x minus 0. And this is twice as long, so it's 2 times that. So let's go ahead and set up our integral, find the volume using the shell method. So far we haven't needed our calculator at all, but we will when we integrate it. So it'll be 2 pi integral from the region starts here at negative 2, stops at positive 2. And then we have a radius, which is 4 minus x, times the height, 2 times the square root of 4 minus x squared, all times dx. If you want to, you could pull the 2 out of there along with the 2 pi, but you don't have to. So let's just evaluate this using our calculator. In this case, we didn't really need it to graph it for us, just this last part. So we've got 2 pi, and then times math number 9, integrate, so it'll be open parentheses again, 4 minus x, close parentheses, times 2 times, the square root of 4 minus x squared, close parentheses, and then comma, variables x, lower limit -2, comma, upper limit 2, close parentheses. We get 315.827. Again, it would be units cubed. And again, let's go ahead and look at using the Nspire real quick. So here I just use this same one here since we didn't need to enter the graphs in at all. So it'd be 2 pi times the integral from -2 to 2, open parentheses, 4 minus x times 2 times square root 4 minus x squared dx. So we get the same answer using the Nspire. And that concludes the notes for AP Calculus on the topic of volume using the shell method.